Fotini, I'm obsessed with time. I feel like St. Augustine, who said when he doesn't think about time, he knows what it is. When he thinks about time, he has no idea what it is. Yet my physicist friends, like you, tell me that you can explain time and that time isn't real and it's derivative out of other things. That seems incomprehensible. So help me understand how theories of quantum gravity on which you work can help understand why time is not real.
I think that time is real.
Oh, okay.
I also have the distressing experience of talking to physicists and they tell me that time is not real.
Oh, okay.
And it confuses me a great deal. Because it seems to be real, things happen.
Right.
So, in fact, I feel even better than St. Augustine. He thought that he didn't know what time is, but you do know what time is. Something happened, I clap my hands, it happened, that's it.
Okay.
Is a time, if you like, is a collection of processes. Those processes can be quantum or classical, whatever they are, but it's a collection of all those processes that makes up time.
But a lot of physicists say time is not real.
I have no idea what they mean. Okay, so strictly speaking, if you are going to look at general relativity, there are some ways to state the theory so that it looks like time is not real, that time does not exist. But this does not take into account many things. For example, it seems to work, the statement that time does not exist seems to work best if you happen to live in a universe with no matter. And it's true that Einstein's general relativity has solutions that are universes with no matter, but we don't live in one of those. So I would prefer to say that general relativity is not the final theory than say that time does not exist.
Okay, so you would privilege general relativity over time in terms of which one is important, because we live in a universe that does have matter.
Yeah, the universe has matter. The universe has matter that obeys the rules of quantum mechanics. In quantum mechanics, there clearly has to be a time, and I would take that over general relativity.
Right. Yeah, so because in quantum mechanics, you have to have time. Time is very important. In general relativity, time is much less important. Time, it's space-time, it's all together. It's a four-dimensional block universe. Time is not a fiction, but it's something very different than we experience. And so that's the tension between quantum theory and general relativity is the nature of time.
Yes, in many ways. So in that sense, so when we work in quantum gravity, we somehow have to reconcile general relativity and quantum theory. And there are, roughly speaking, two possibilities. One is to take general relativity and quantize it and make a quantum space-time, if you like, or a quantum form of time. And there it would be more natural to worry about the problem of time does not exist in some sense in general relativity, so how could I make a quantum version of that and compare it with the world that I know?
Right.
The other possibility is that you start with quantum theory, where there is a clear notion of time, and try to show how general relativity may be emergent as a collective behavior of all the matter that obeys the rules of quantum theory. So then it will, if this is the path that turns out to be true, it will not be the case that time does not exist. It will only be the case that in some approximation where general relativity of an empty space-time is the relevant approximation, then you may worry about time not existing. But in the very fundamental theory, you will just have quantum theory, and there is time there.
In your own theories of quantum gravity, what happens?
Pretty much is along the direction that I was describing to you. You start with quantum mechanics, but you cannot, the catch is that you cannot start with space-time. So you have to have some description of the universe before there was, for instance, space. So how do you describe the world before space? So what we have instead of quantum systems in space, we have quantum systems on a network. And the network is basically telling you who is interacting with whom, which you can think as a more primitive notion of space.
And this concept of network comes before space-time?
That's right. So then the idea is that if the network organizes in such a way that you have symmetries that we associate with space, such as translation symmetry, rotation, or Lorentz symmetry, and so on, then you say that space geometry emerges.
But time is there.
Time is there.
Right. So you've disaggregated space and time.
That's right.
Which contradicts general relativity?
Yes, so it makes people that work on general relativity very upset that we make this separation
I
between
can't imagine
space
you
and
making
time.
anybody that upset.
Right. No, I mean, it has. In many ways, the lesson from general relativity is that space-time is one object.
Right.
But there is a way in which this may be a misleading lesson, because yes, it's true there's a four-dimensional geometry, but this four-dimensional geometry, there are many ways in which it does treat space different than time.
Yes.
So it is not true that time and space are interchangeable. There are fundamental differences. So I think
even
it's fair
within
to split them.
relativity.
Even within relativity.
But you take it a huge step further. You split time.
Yeah, we
and
totally
space and
split
time.
it. That's right.
Totally split it.
That's right.
And you privilege time over space.
Yes, we basically the strategy is that you could conceivably, I don't know, because it's not as if we have achieved the quantum theory of gravity,
Sure,
right? So
sure,
this is
sure.
all tentative. But perhaps you can construct a consistent theory where time exists all the way at the fundamental level, but the price is that space does not exist. So space has to be not fundamental. And in many ways, this is not such a big deal, because space not being fundamental is not as mind-blowing as time not being fundamental. Well, so at the end of the day, in general relativity, at least in a universe with no matter, there is the conceptual problem that in a way it looks like time does not exist, while in quantum theory there is a very clear notion of time. So our hope is that you could perhaps solve this contradiction between the two by saying that time does exist at the fundamental level, but what does not exist is space. So you may try to instead have a description of the world where the universe is a collection of quantum systems, as we normally think, except the quantum systems do not live in space, as is the usual way, but they live, say, in a network in our models. And the network is the precursor of space. So there are particular configurations of a network that will make you call it space. So if the network is, for example, a regular network, then you would say it's flat space.